Okay, this is the key for the Unit 11 practice exam. I'm going to go through it pretty quick, but you can always ask me questions if you have any questions about anything. So, first multiple choice question, which of the following materials has the ability to hold more heat per unit temperature? Well, for this one, what you're looking at is the specific heat and trying to figure out which one has the largest specific heat. So look at your table and you should see that D, iron, has the largest specific heat. And specific heat, I should say, is short for specific heat capacity, which means how much heat can something hold. So iron here is going to hold the most. A small child wanders out into the cold and releases heat into the environment. If we're focusing on the child, is she exothermic or endothermic at this time? Well, she would be losing heat or giving off heat into the environment, so that would make her exothermic. Which of the following best defines enthalpy of a substance? Enthalpy, if you look through your notes, and I recommend you looking through all of your notes before you take this test, enthalpy is the amount of energy that's stored inside the bonds, mostly, of a substance, also stored inside its volume and pressure, but mostly in the bonds. So looking through that, make sure you kind of understand those other things as well. The amount of thermal energy stored in a substance is related to kinetic energy or the motion of its particles or its temperature and things like that. The state of relative disorder, that's talking about the entropy, the transfer of heat between two substances due to a difference in temperature. That one is heat. Okay? So, number 4 here. Describe the following situation in terms of heat. A high temperature object is separated from a low temperature object by a perfect insulator. So for this one, you have to know that heat is defined as the flow of temperature between a hot substance and a cold substance, or a substance of high temperature and a substance of low temperature. Because this is perfectly insulated, no heat is going to occur here. There's going to be no transfer of thermal energy. So D is the correct answer. All right, which of the following is true for an endothermic process? So the first thing here, is energy coming in from the surroundings or is it being transferred out? In endothermic, energy is coming in from the surroundings. What that energy is doing is it's going and being stored in the bonds. So enthalpy is going to be increasing in this case. So B is the correct answer. Number 6, the entropy of a system is slightly increased while the entropy of the surroundings is highly decreased. Okay, this is getting at the second law of thermodynamics, which says the entropy of the universe always increases with any spontaneous process. Well, the universe consists of the system and the surroundings. Here it says the system is slightly increased, the surroundings are highly decreased. So you should see that we get a net decrease in entropy here. Well, that goes against the second law of thermodynamics, which says the entropy of the universe needs to increase. So this is a non-spontaneous process, which means that it would not happen naturally. All right. You see an apple in front of you fall down from a tree. What's true about the entropy of the universe in this situation? So in this situation, basically anything that you actually observe needs to be following the second law of thermodynamics. It's a law in science. It has to be followed. And so if you've observed it, that means the entropy of the universe has increased. Going on, it says, which of the following has more entropy? Looking at this, entropy again means dispersal or disorder or something along those lines in chemistry. So if we're looking at molten copper, which is liquid, and solid copper, which is solid, liquids have more entropy because they're more spread out, they're hotter probably, things like that, which means the particles are moving around more. More possible states are accessible, so this one is going to be A. This is looking at the following reaction, which has more entropy, the reactants of the products. In this case, we've got a solid and a liquid going to a solid, so that should indicate a decrease in entropy, all right, because entropy is disorder or dispersal. The other thing is we've got 3 moles of substance on the left-hand side, on the reactant side, because we've got 2 moles of sodium and a mole of chlorine, and we just have 2 moles on the product side. So that's 2 moles of NaCl. So if we can have 3 things instead of 2 things, we can disperse them in more sorts of patterns, and so, having 3 moles on the products, or on the reactant side, means that there's going to be more entropy on that side as well. So that's 2 reasons why the reactants have more entropy. Number 10, if the bonds are broken in a reaction, have more energy than the bonds that are formed. The sign in delta H is. For this one, you have to remember that breaking a bond requires energy. And as bonds are formed, it releases energy. And so it's saying that more energy goes into breaking bonds than is released. Okay, so that means more energy is coming in. If energy is coming in, then it's an endothermic process, which means delta H is positive. On to page 2, it says the following energy graph shows that the reaction is, and here we see that the reactants have more energy than the products. If the reactants have more energy than the products, that means energy must have been lost or given off in this process. If that's the case, then it is exothermic, which is B. Which of the following is an example of potential energy? Potential energy is stored energy versus kinetic energy, which is energy of something has that's in motion. So looking at these, we've got energy of the Earth rotating about its axis. Rotation is motion. Okay, so it's not A. Looking at B here, energy the Earth has flying about in space. So that one also, flying is moving, so that's kinetic energy. Energy the Earth has from being hot at its core. Now this one is a little bit confusing because you don't see large macroscopic motion in this case, but what's going on is you've got that microscopic motion, the motion of the particles. And so being hot is high temperature usually, and that means that the particles are moving around a whole lot, and so that's related to the kinetic energy as well. So by process of elimination, we can see that it's D, the energy that the Earth has from being attracted to the sun through gravity. The other thing here is that gravity is just listed on your different things that create potential energy on your thermodynamics note set. So if you're confused by that, make sure that you're familiar with the common types of potential energy and common types of kinetic energy. Question number 13. Which of the following is not a place where energy is stored in a substance's enthalpy? Well, enthalpy is the potential energy of a chemical, and it's usually stored in the bonds or the pressure or the volume of the chemical. All right. Movement is kinetic energy again, so that one is not potential energy anyway, so that's going to be the answer there. Putting a sweater on a snowman would cause the snowman to. This one's sort of a tricky question. We went through an example in class, and I said if you had a snowman and you put it out on a hot summer's day and you put a coat on it, would it make it warmer or would it make it stay cool? And the answer to that question was that it would stay cool. But in this case, I haven't told you about anything with the weather outside. So if the weather was really, really cold outside, colder than the snowman is itself, then it would allow the snowman to stay warm. If the weather was really, really hot outside, it would allow the snowman to stay cool. It's kind of like a thermos is an insulator. You can put really, really cold liquids in a thermos and they'll stay cold. You can put really, really hot substances in a thermos and they'll stay hot. So an insulator keeps things the same temperature that they are, but it all depends on the surroundings in this case. And so since we don't know how hot it is, we can't answer this question. Number 15, the symbol used to represent entropy is S. That's A. And so looking there, the other symbols, H is enthalpy, E is energy, and Q is heat. So make sure you actually know what all of those are. All right, so down here to the problem section of this, we've got this first one here is a Q equals MC delta T problem because it's given us some information about heat and change in temperature, but we only have one thing here. It's not a calorimeter. So first you have to figure out what it's asking for. It says, what's the mass of the bar? So we know that mass equals Q over C delta T, which equals, in this case, 45. And then we have to look up the C for iron. It's 0.444. All right, delta T in this case, it's going from 25.0 to 100.0. because those are both to the tenths place, our answer here should be to the 10th place, 75.0. All right, and then what we have here, 2 sig figs on the top, 3 sig figs on the bottom, times 3 sig figs. And so we have 2 sig figs in our answer. What you end up getting then is 1.4 grams. All right, which is option B. Number 2, this is a calorimetry problem you can identify, which means that we're going to use the equation negative mc delta T equals mc delta T. This time it's asking us for the original or initial temperature of the water. Anytime that I ask you for an initial temperature or a final temperature, I'm going to tell you that you can ignore sig figs. Basically, just it's a more algebraically complicated problem, and I don't want you to have to deal with all the sig fig mess while you're also dealing with all the complicated algebra. So this one we're not going to pay attention to sig figs. So plugging things in here, I get negative 35.0 for the mass, times C for silver is 0.237, times delta T, the silver. It goes here from 200 degrees Celsius, that's 200 points, so it's to the ones digit, to 35, which is also to the ones digit. Oh, I guess we don't really care about sig figs here, but it's good practice to kind of think about that. So this ends up being negative 165 equals mc delta T for the water, that's 81.7 times 4.184 times 35 minus Ti. And so in this case, this relies on you knowing that delta T is defined as T final minus T initial. All right, and so we've just plugged in the final temperature but left them separate. So you can do some simplification here. Find on this side that we've got 1368.7 equals 341.8 times 35 minus Ti. Okay, we distribute that 341.8 through to the 35 and the negative Ti, and I get 1368.7 equals 11,963 minus 341.8 Ti. I bring all the Ti's to the left-hand side. I subtract 1,368.7 from both sides to get that over to the right-hand side. And the next thing that I end up with is 341.8 Ti equals 10,594.3. Divide both sides by 341.8, and I get that Ti equals 30.9956 degrees Celsius. It's important to note on this one that I said that you're ignoring sig figs, so that answer, you don't see it down here, but if you look at the possible answers, it would round to be answer B, so answer B is correct in this case, since we're not paying attention to sig figs. For problem number 3, this is an enthalpy problem. What we've got here is we're going from liters of a substance and we're going to Q, so liters to moles to Q. Liters to moles, 22.4 is the conversion factor. Moles to Q, delta H, and the ratio are your conversion factors. So that's how this sets up. Starting here, 25 liters on top of O2. We know that there's 22.4 liters of O2 in 1 mole of O2. All right, and then looking here, we see the coefficient on O2 is 1. So for every 1 mole of O2 that's produced, we absorb 181 kilojoules. We're going to have 2 sig figs in this problem because 25 liters has 2 sig figs. That the 1 mole O2 on both of those cases, that ends up being infinitely many sig figs because in the case of the 22.4, that's a perfect mole. The definition, the 22.4 is where we have the sig figs. And then the 1 mole O2, that's that perfect ratio on the bottom there. And so that's infinitely many sig figs as well. So we calculate this to 2 sig figs. And you see there's a bunch of similar answers here, but the one that has the correct number of sig figs is D. So we put that little bar above it to indicate that the 2 in that first 0 are significant, but the second 0 there is not significant.